In the last few slides, we saw how under-constrained problems can be avoided. We also saw the relevant ANSYS tools and settings to ensure that the contacts are appropriately detected and closed. Now, we are going to see how convergence problems arising due to a sudden change in stiffness during the contact closure are to be handled. Generic guidelines to facilitate better convergence are as follows. 1. Keep automatic time stepping on. 2. Use large number of substeps. 3. Appropriately specify the contact parameters, like normal stiffness factor, penetration tolerance, and chatter control. And 4. For penalty or augmented Lagrange method, initially, keep a small normal stiffness factor. If the solution is converging, it can be progressively increased. We are going to learn more about the above-mentioned contact parameters in the subsequent slides. Following parameters are commonly adjusted to facilitate better convergence. 1. Normal stiffness factor. 2. Penetration tolerance. And 3. Chatter control. The first two parameters can be changed from the advanced branch of the details window of the contact pair. Chatter control can be adjusted using the command snippet. We are going to see what is the normal stiffness factor and how it can facilitate a better convergence. Recall that in the penalty and the augmented Lagrange method, no penetration condition is achieved by introducing the separating force that is proportional to the penetration and the contact stiffness. In the mathematical terms, the separating force lambda is equal to the contact stiffness Kn multiplied by the penalty function phi n. The contact stiffness is further represented as Kn equal to Fkn multiplied by Kns, where Kns is the contact stiffness and Fkn is the scaling factor. Fkn can take only positive values. If Fkn is set to negative, it is considered as the contact stiffness and not the scaling factor. By reducing Fkn, contact stiffness is reduced, and by increasing Fkn, the contact stiffness is increased. The effect of a normal stiffness factor is demonstrated using an example in this slide. Fkn values greater than 1 result in a larger contact stiffness, and hence, lower penetration. However, it results in convergence difficulties. Fkn values less than 1 result in a smaller contact stiffness and ease of convergence. However, penetrations are higher, which can make the contact results unrealistic. A 2D contact model is shown in the figure below. A semicircular plate is pressed against a flat surface. In the first case, Fkn is very small, around 0.01. This results in a large penetration of around 5 microns. However, the solution converges quickly in 2 iterations. In the second case, FKN is increased to 5. This results in a higher contact stiffness and lower penetration. The convergence is marginally difficult, but the solution converges in 3 iterations. The penetration is drastically reduced to 0.015 micron. In the third case, FKN is increased to 10. This further increases the contact stiffness. The contact becomes so stiff that the solution does not converge in more than 100 iterations. Thus, an optimum FKN value is recommended to balance penetration and the ease of convergence. In the last couple of slides, we learned about the normal stiffness factor. The normal stiffness factor is only relevant to the penalty or augmented Lagrange method. In the normal Lagrange method, zero penetration condition is enforced. Numerically, it is impossible to achieve a penetration value of 0. Therefore, the solution often oscillates between contact status open and closed. This is known as contact chattering. Contact chattering can be controlled by 2 additional parameters. 1. Penetration tolerance, and 2. Maximum allowable tensile contact pressure. Penetration tolerance is the tolerance value for the penetration. If the contact penetration is less than the penetration tolerance, the contact status is assumed to be closed, and no separating force is generated at the interface. Similar to the normal stiffness factor, penetration tolerance, or FTOLN, is a scaling factor. By default, FTOLN is 10% of the depth of the underlying elements. Similar to FKN, if FTOLN is positive, it is considered as a scaling factor. If it is negative, it is considered as the permissible penetration value, and not the scaling factor. Similarly, if the tensile contact pressure in the contact pair is less than the maximum allowable tensile contact pressure, the contact is kept closed, even if there is a separating force at the interface. Note that ideal contacts do not support tensile load, and they separate to open the contact, as the tensile force is generated at the contact interface. Maximum allowable tensile contact pressure is the tolerance provided to keep chatter under control by delaying the change in contact status from closed to open. Similar to the normal stiffness factor, maximum allowable tensile contact pressure, or TNOP, is a scaling factor. By default, TNOP is 1% of the force convergence criteria divided by the contact area. Similar to FKN, if TNOP is positive, it is considered as a scaling factor. If it is negative, it is considered as the permissible tensile pressure value, and not the scaling factor. Maximum allowable tensile contact pressure can only be changed using the command snippet. The command for changing the TNOP of a contact pair with the real constant number, CID, and the modified TNOP factor of 0.05 is shown in the slide. This should be entered in the command snippet below the contact branch of interest.